A very good afternoon, everyone. Welcome to the first Biointegration Academic Seminar of the 5 regions of China. And today we are on the first 5 regions, and it's actually going to be based in Wuhan. But due to the pandemic situation, we're now going online. But nevertheless, today we have with us 7 very prominent speakers. And I would like to introduce them and their title for today. So first, we have Dr. Jason, and he's actually currently in Portugal. He is a postdoctoral research fellow, and he focused on application of nanobiotechnology, especially in diabetes. And it's quite amazing that he has authored about 25 book chapters. He wrote about 33 journal articles, and also he edited a book for Nova Science Publisher. And today he's going to share with us on the emerging nanomedicines for diabetes treatment. So let's welcome him.
This presentation is divided into 4 parts. In section 1, I'm going to introduce about nanomedicine. In section 2, I'm going to introduce about diabetes and its conventional treatments and how nanomedicine is going to be helpful. In section 3, I'm going to mention about my research projects, and in section 4, I'm going to mention about my current projects and invitation to collaborate. Let me start the presentation. So, introduction to nanomedicine. What is nanomedicine? As we all know, particles with the size of 1 to 100 nanometer is considered as nanoparticles. In certain cases, 1 to 1000 nanometer sized particles are also considered as nanoparticles. Similar to nanoparticles, medicines in the size of 1 to 100 nanometer or 1 to 1000 nanometer in size is known as nanomedicine. So what is nanomedicine? If you take a conventional medicine and fabricate into nano-sized medicines, it is termed as nanomedicine. Or if you have a conventional medicine and if you formulate it into a nano-sized particle, it is also considered as nanoparticles. The basic criteria here is if you reduce the size, its property should differ. So that's the only criteria to call them as nanomedicine. For example, in the first case, the example is if you have nanomedicine, for example, doxil or metformin or something, and if you fabricate them into a nanoparticle, nano-sized metformin, nano-sized doxil, which is called as doxorubicin. So those things are called as nanomedicine. In other terms, if you have a metal or polymer or a metal oxide nanoparticle and formulate them into a nano-sized liposome or micelles, it is also termed as nanomedicine. So what is the significance of this nanomedicine? Most of the biological macromolecules such as mitochondria, ion channels, secretory granules, lysosomes are nanostructures. So it is easier for these nanomedicine to target these nanostructure, engineer them, repair them without having any side effects, and also have more bioreactivity. So that's why these nanomedicines are used as controlled and target drug delivery system in bioimaging, in biosensors, in biomarkers, biomarker mapping, gene delivering, molecular imaging, and in several biomedical and pharmaceutical applications. This slide shows the history of nanomedicine. The history of nanoparticles started in 1905 when Einstein estimated the size of sugar compound as 1 nanometer, and it took about 90 to 100 years for Sumio Ijima to invent carbon nanoparticles in 1991. And in 2000, many countries have developed their nanoforums to develop projects on nanoparticles and everything. And in 2009, nanoparticles have been used as a targeted drug delivery system to cancer tissues in vivo condition in mice models. And from 2016 until now, more studies are moving towards nanotoxicology, as nanoparticles or nanomedicines are entering into commercial space, and more it can affect environment or human or other living organisms. So that's why currently it is moving towards this phase. This slide shows the history of nanomedicine in brief. From 1964 to 1994, this is considered as an era of conceptualization of nanomedicine. In this time period, liposomes, dendrimers, polymeric nanoparticles, micelles, everything was considered as the materials or agents to formulate nanomedicine, or conventional medicines formulate into these type of polymers. So that conceptualization era has led to the clinical validation and commercialization era from 1995 to 2007. So this area, in this time period, many particles have been developed and they have also clinically validated, and they move towards a commercialization and FDA approval and so on. From 2008 to 2011, this clinical validated nanoparticles or nanoformulations as nanomedicine has been expanded and refined for several biomedical and pharmaceutical applications, and from 2016 it has been moving towards nanotoxicology era. Why nanomedicines are special? Why researchers are highly motivated towards nanomedicine research? As I said before, to call a medicine as nanomedicine, it should be under 1 to 100 nanometer in size, or 1 to 1000 nanometer in size, whatever, but its property should differ from that of a conventional medicine. This property difference is because of two aspects. One is high surface to volume ratio, which is related to its size. When you reduce a bulk material into a nanomaterial, its surface properties differs. For example, if you have a bulk material like this, only 4 atoms are exposed to the surface. But in the same volume of a material, you will have several nanoparticles since you reduce the size, and because of its size, you will have not 4, you have 14 or 16 or several hundreds of atoms which is exposed to the surface. Because of this high surface to volume ratio phenomenon, its bioreactivity is higher, its bioavailability, its biodegradability is higher, because of which nanomedicines are special. The second one is related to its shape. In this slide, I have shown the different shapes of nano zinc oxide nanoparticles. It can be fabricated into ring, into hexagon, into fibers, and several other shapes. And depending upon shape, also nanomedicine's property will differ. So that's why when the property of a nanoparticle, when the size and shape of a nanoparticle differs, its property differs, and because of which nanomedicines are highly fascinating for researchers to research on. In the previous session, I have summarized the importance of nanomedicine. So in this session, I'm going to introduce about diabetes and what are the conventional treatments and how nanomedicine can be helpful in the treatment of diabetes. So what is diabetes mellitus or diabetes? Every day we are taking food. Food is required to give you energy to do any activity. So once you take the food, it goes to the intestine where it gets digested, and because of the digestion process, it is converted into glucose, and this glucose is taken to all the parts of the body, all the cells of the body through blood. So this is how the glucose goes to all the cells, and this glucose should be converted into energy form, into ATP, which I will say in the later slides. So this glucose will be converted into energy, which is required for the cells to activate, to work, to provide you energy. So this glucose in diabetes, this glucose level will increase in blood, which will increase the viscosity of the blood, and because of the increase in viscosity, this will affect the flow of blood, and which will cause a block in blood vessel or blood pressure. So in general, diabetes is a disease where blood sugar level, blood glucose level increases for a prolonged time period, not for a short time period, for a prolonged time period. So it should be for at least 6 months or 1 year, it should be in a rise, it should increase. So why do we need to worry about increase in blood glucose level? Because increase in blood glucose level will lead to block in blood vessel or increase blood pressure. So in Asia, in average condition in Asia, before meal it should be the blood glucose level should be 4 to 5.9 millimole per liter, and after meal it should be below 7.8 millimole per liter. And if this level is increased for a prolonged time period, it is called as diabetes mellitus. In general, diabetes is classified into two types. One is type 1 diabetes and another one is type 2 diabetes. In type 1 diabetes, the body's inability to produce insulin. So your insulin, the pancreas will produce insulin, so your pancreas will have a malfunction, so because of which insulin will not be produced in these type of diabetes. But in type 2 diabetes, insulin will be produced, but your cells cannot respond or fail to respond to insulin properly, which is a condition called insulin resistance. So that is type 2 diabetes. In type 2 diabetes patients, insulin will be secreted, but it cannot be utilized by the cells. And there is a third type, which is gestational diabetes, which is also similar to type 2 diabetes, but it occurs only in pregnant women during pregnancy. So what is insulin, its function, and insulin resistance? We will see in next slide. Insulin is a peptide hormone, a protein in endocrine system produced by beta cells of pancreas. This figure shows the mechanism of insulin. As I said before, after you intake your food, it goes to the digestive system. In intestine, it gets digested and it gets converted into glucose, and it is taken to all the parts of the body or the cells of the body through blood. So once the glucose enters into the blood, insulin will be secreted by the pancreas, and it is also taken to all the cells of the body through bloodstream. So from the bloodstream, insulin will also enter into your cell. So this glucose meets the insulin and gets converted into pyruvate. Pyruvate will be converted into fatty acid, and fatty acid to ATP, adenosine triphosphate. So this ATP gets stored in the mitochondria of the cells, which is powerhouse of the cell, and from this mitochondria, a cell will get energy for its function. So for the conversion of this glucose, insulin should be present inside your cell. As I said before, in type 2 diabetes, this insulin will be secreted, but it will not enter into the cell as there will be a block in this insulin receptor. So this term is called as insulin resistance in type 2 diabetes. This slide shows the timeline of anti-diabetic drugs developed throughout history. In 1923, insulin has been developed, and from 1923 to 1956, several insulin types has been developed to improve their efficacy. And later in 1956 and 1959, metformin and tolbutamide has been produced, and this type of drugs has been used to degrade glucose into ATP in the presence of insulin. So it goes along with insulin. So it's like a combination treatment for diabetes. But this will lead to hypoglucose condition, so reduction in glucose level in the blood, so which will lead to anemic condition and so on. Later in 1955 to 2013, several drugs has been produced, which is to convert this glucose into ATP without the presence of insulin for both type 1 and type 2 diabetes patients. But all these drugs has led to one type of side effect or another, like increase in obesity or increase in blood pressure or decrease in blood pressure, or increase insulin condition, or insulin or damage in the cells, and so on. Because of the drawbacks in conventional drugs, several researchers propose that nanoparticles or nanomedicines can be beneficial for the treatment of diabetes. Swinton et al. In 2009 showed that insulin therapy or treatment with conventional drugs to convert glucose into ATP can lead to hypoglycemia, which is decreased blood glucose level, and weight gain. This is because in all these studies they have used high concentration of insulin or conventional drug in those treatment models. So that's why nano formulations have been used for the controlled delivery of insulin. For example, pluronic F127 for buccal insulin delivery, insulin-loaded polymeric nanoparticles for oral insulin delivery, chitosan nanoparticles for oral insulin delivery, and chitosan-reduced insulin-loaded gold nanoparticle for nasal delivery of insulin has been used for the controlled delivery of insulin. Until now, all the nanoformulations have been used only for controlled delivery of insulin. This type of treatment can be useful only for type 1 diabetes. As I said before, in type 2 diabetes, the problem is insulin resistance and not insulin secretion. That's why in my projects, I'm using a nanomedicine as a supplement to reverse this insulin resistance. So I will explain about my project in the next session. In session 3, I'm going to explain about nanomaterials to reverse insulin resistance in type 2 diabetes treatment. Nanoformulations have been useful for controlled delivery of insulin, as I mentioned in my previous sessions. But nanoparticles as nanomedicine has been useful for certain diabetes treatment applications. For example, gold nanoparticles are useful for bioimaging of diabetic cells, and gold nanoparticles are also useful as a glucose sensor, as a biosensor for monitoring of glucose in diabetic patients. Silver nanoparticles, for example, they are useful for antimicrobial activity, especially in diabetic foot ulcer treatment. But the limitation of these metal-based nanoparticles, they are not stable and they get oxidized easily. For example, silver can be formed into silver oxide. So that's why we prefer metal oxide nanoparticles compared to metals, as they are stable and they are biologically active and biocompatible than metals. However, most metal oxide nanoparticles are used only for insulin delivery, as I mentioned before. For example, copper, zinc, manganese, titanium, and cerium oxides. And composites and biometallic nanostructures are used in glucose biosensors. Why magnesium oxide? So in my work, I'm going to use magnesium oxide nanoparticle as a magnesium supplement to reverse insulin resistance. So why magnesium oxide? Kandil et al. In 1996 showed that magnesium sulfate can reverse insulin resistance. But in that work, he used high concentration and it takes 48 hours. And May et al. In 2004 showed that high concentration of magnesium can cause cell proliferation. It can lead to cell development. And Probagallo et al. In 2003 showed that insulin resistance due to low magnesium level. There is a correlation between insulin resistance and magnesium level. And he also mentioned that magnesium is needed for the activation of enzymes, but he didn't mention which enzyme. And G et al. And several other studies show that magnesium oxide nanoparticles are non-toxic to human cells and magnesium nanoparticles are stable in body fluids. Because of these reasons, magnesium oxide nanoparticle has been selected to reverse insulin resistance in type 2 diabetes. So the aim of my project was to study insulin resistance reversal ability of non-toxic MgO nanoparticles as magnesium supplement to treat type 2 diabetes. In the previous study, Kandil et al. In 1996, so consider this one as an insulin resistant cell, diabetic cell, right? So in that work, he used magnesium sulfate, and this magnesium sulfate will bind with the surface of the cell and it disintegrate into magnesium plus and sulfate ions, which will activate extracellular enzymes. But in the current study, in my project, I've used magnesium oxide nanoparticle. So this nanoparticle can bind with the surface of the insulin resistant cells and also enter into the cells, into the diabetic cells, and activate both extracellular and intracellular enzymes and reverse insulin resistance and make insulin to enter into the cell. So glucose will also enter into the cell, so it will convert glucose into pyruvate, pyruvate to fatty acid, and fatty acid to ATP, so the cell will get energy. So a diabetic cell will be converted into a normal cell in type 2 diabetic patients, provided they have perfect insulin secretion. So the significance of the study is the synthesis methods in my study has yielded different morphologies. I have used chemical synthesis method as well as green synthesis. In chemical synthesis, I have used Sol-Gel method, and in green synthesis, I have used aqueous extract of certain plants. And morphologies like hexagon and rod shape can facilitate entry of nanoparticle into cell. So different morphologies included spherical, hexagon, and rod, and we have identified that hexagon and rod shape can facilitate entry of nanoparticle into cell. So in this hexagon, hexagon is transformed into an extended hexagon, which is in a type of rod. So I will mention about later, or you can read our previous manuscripts. Cytotoxic study will help in screening toxic nanoparticles. So we have used double stage cytotoxic analysis by using diabetic cell lines, 3T3L1 cells, as well as Vero cell lines, kidney cell lines. So normal cell and diabetic cells. So in both these cell lines, the selected nanoparticles are non-toxic or less toxic. And the major significance is the development of nanoparticle that can reverse insulin resistance without any side effect, as we are going to use only a few doses of nanoparticle and it takes only 24 hours. As magnesium oxide is synthesized in nanoform, less concentration will be needed for reversing insulin resistance. So the novelty of the study, development of different morphologies is first novelty. So we have synthesized spherical, hexagon, and rod by using chemical synthesis, and we have developed spherical and hexagon shaped nanoparticle by using green synthesis methods. Previous studies focused on spherical shaped MJ nanoparticles using Sol-Gel, but in our method we have produced hexagonal and rod shaped MGO, which has the ability to penetrate into cell and activate enzymes. And green synthesis of magnesium approach to reduce toxicity. So this is the first time we have synthesized magnesium oxide nanoparticle by using a green aqueous crude extract of certain plants, Andrographis paniculator, green spinach, and red spinach. And this is the first work to use nanomaterial to reverse insulin resistance. So this is the major novelty of the present study. So here is the results of our study. You can see our results in these two articles. So this shows the cytotoxic analysis MTT assay in both 3T3L1 and Vero cells. Sample B is Sol-Gel synthesized hexagonal shaped MGO nanoparticle, and this is sample GA is from Andrographis paniculator. From Andrographis paniculator, sorry, not Andrographis paniculator, like Amaranthus tricolor, the red spinach one, and it has been transformed from spherical to hexagonal by using pH alterations. Right, so the hexagonal shaped green synthesized MGO nanoparticles, the results are present here. So this shows that in diabetic cell lines they are less toxic, but in normal cell lines they are almost non-toxic, and especially green synthesized ones are less toxic compared to the Sol-Gel synthesis one. The main important result is here. So compared to the control, the green synthesized MGO nanoparticle has reduced has reduced both the green synthesized and the chemical synthesized nanoparticle both reduce the glucose present in added in the diabetic cell lines by with the help of insulin. And this takes only about 25 hours to reverse insulin resistance, to reduce the glucose by reversing insulin resistance. And the Western blot analysis also showed that blood protein has been expressed uh, in those uh, in those samples. So you can read the results in these two papers. These are the news articles where our research has been acknowledged. This is a news article in Malaysia. Innovative Malaysia in the Star newspaper, they have acknowledged our research, and in several platforms as well as internet news articles. These are the research articles which we have published related to our project. And we are also currently working on aptamer navigated copolymeric drug carrier system to deliver these MgO nanoparticles. So our idea is to encapsulate these MgO nanoparticles to target only diabetic cells, to reach the diabetic cells, release MgO nanoparticles, and reverse insulin resistance in only in diabetic cells and leave out normal cells. So our current projects and possibility for collaborations. So currently I'm working on dendrimer formulated MgO nanoparticles for biological applications. So since MgO nanoparticles have been working for about 5 years, so currently I'm going to work on to stabilize these MgO nanoparticles by using dendrimer formulations, and also to use them as a drug carrier system to reach diabetic cells or cancer cells, to reverse insulin resistance, or as an anti-cancer ability. So currently I'm working in University of Madeira. It is in the city of Funchal, Madeira, Portugal. It is a Portugal government university. For those who doesn't know, Portugal is here and Madeira is in the center of Europe and Africa. So we are here. It is a small beautiful island. And this is our main campus, which is built in 16th century, and this is a new campus which has been built in 1988, and our department is in the ground floor of this building. And this is our center, CQM, Centro de Química de Madeira, and I belong to Molecular Materials Research Group. The core research area of this group is dendrimer formulation for drugs and nanomedicine, and we also synthesize carbon nanomaterials. And currently I'm working on dendrimer formulation of MgO nanoparticles for both cancer, for anti-cancer activities, as well as diabetic treatment. And we invite all young collaborators, so those who are working in diabetic cell lines or animal models, so those who want to work in this field to test this, to help us to test our nanoparticle or dendrimer formulated nanoparticles. You always welcome to contact me. My other research interests are we are also developing and evaluating glucose responsive nanogels for type 2 diabetes, and this is a collaborative project with BIOI Limited, Bangalore. It's a company, it's a small scale biotech company in India, and we are also working on nanoparticles as light mediated antibacterial paints. So there are two projects in chemical engineering department, Curtin University, Malaysia, my alma mater, and antibacterial study of charge and concentration specific purified endotoxin towards E. coli and Pupitida. This is a collaborative project in University Malaysia Sabah, Malaysia, and we are also working in novel coronavirus biosensor using aptamer. It is a in silico model. We are working on in silico models with Professor Michael in University of Tennessee at Chattanooga, USA, and we are also working on drug repurposing for treatment of COVID-19, which is a project funded by Indian government with ACRT Biotech. It is also a small-scale biotech company in India. So about me, I am Dr. Jason, as you all know. I studied, I did my bachelor's in zoology and biotechnology, and later I moved towards masters in nanoscience and MBA, masters in business administration. Human resource management is my area. All these until masters, I did my studies in India, and then I moved to Malaysia, where I did my PhD in Curtin University, Malaysia, and the project which I was working on and still I'm working in was funded by Curtin University, Australia, and yeah, so all the results and everything was from that time period. And I have experiences in nanoparticle synthesis, especially green synthesis of plant particles, of plant extracts, characterization of nanoparticles, cytotoxicity analysis, and as well as in vitro diabetic studies. And current research, I am focusing on using application of bio nanotechnology for the fabrication and nanoformulation of drugs for the treatment of several diseases, especially diabetes and cancer. And till date, I have authored about 36 book chapters, 45 journal articles, and edited a book for Nova Science Publishers, and several conference papers. And my previous past careers, past research experiences are in Curtin University, Malaysia as a research associate, and MKD Labs with Professor Michael as a research consultant. And currently I'm also editing and writing certain books for Elsevier, United Kingdom, and currently I'm working in as a senior researcher in University of Madeira. And these are our books. This book is currently available online. You can purchase them, and this book will be available in December 2021 or in early or probably early in 2022. So I would like to thank Biointegration Journal for the opportunity, Professor Saw, other conveners and coordinators of this Youth Forum 2021, and all the participants for your patience to hear this presentation. And this is my funding agency, so I'd like to thank them for funding my research. And this is my contact, email ID, blog, and my Facebook, how to reach me. And so thank you very much for your patience, and thank you. I am looking forward for your collaborations.
And the fourth speaker for today is a clinician, Dr. Chiwi Mok from Changi General Hospital from Singapore. He's currently a consultant in the Department of Surgery, and his work is mainly on the breast diseases, both benign and malignant. And in Singapore, basically, he has developed two new minimally invasive breast surgery techniques, which one is a three-dimensional endoscopic subcutaneous mastectomy. And today he's bringing to us also an integration approach in the clinical system, which is a multidisciplinary team approach, the crux of breast cancer management in the new normal, which means in the face of the pandemic. So let's welcome Dr. Mo.
Hello, a good day to everyone. First of all, I have to thank the editorial board from Biointegration for inviting me to speak today. And I'll be sharing on this topic that is close to all of us here, I believe. That is how we manage patients in the new normal in the COVID-19 pandemic era. So today, I'll be sharing with all of you the multidisciplinary team approach, which I feel is the crux of breast cancer management in the new normal. I'm Chiwe from Singapore, and I practice as a consultant oncoplastic and minimally invasive breast surgeon. To give a little bit of background, I think all of us would have realized that the COVID-19 pandemic has forced healthcare institutions around the world to direct resources to better manage the pandemic. This has inevitably resulted in a sudden acute limitation of resources to care for non-COVID patients with critical conditions. In Singapore, we are no exception. The escalating situation at the initial start of the pandemic has necessitated swift reaction in the Division of Breast Surgery in Changi General Hospital to develop strategies to support the battle against COVID-19 on one side, and yet deliver care to our breast cancer patients at the same time. This paper that was initially published last year described the challenges faced and measures adopted by the division during this pandemic in our multidisciplinary management of known COVID breast cancer patients. It is therefore our fervent hope that this article will serve as a guide for physicians or surgeons in similar settings who are managing breast cancer patients amidst this pandemic. The first case of COVID-19 in Singapore was first reported on 23rd January 2020. Back then, Singapore actually had the highest number of reported cases outside of China by the end of January 2020. Consequently, the Ministry of Health raised the level of the Disease Outbreak Response System condition, in short known as DORSCON, from yellow to orange, signifying that the disease was severe, spread easily, but was still contained. Containment measures then included travel restrictions, temperature screenings, as well as quarantine for certain groups of people. Unfortunately, the number of COVID-19 positive cases rose alarmingly, leading to the then implementation of the circuit breaker measures by the Singapore government to last for 2 months from April to June 2020. This actually meant the closure of all schools, institutes of higher learning, and non-essential services. Home-based learning and working from home became the new default. Everyone was required to remain at home except when attending to essential needs, and masks were to be worn all the time when going out, and also safe distancing of at least 1 meter was required. The aim then, as what we call it, was to flatten the curve and reduce community spread. So these restrictions also applied to hospitals in order to limit contact between healthcare staff from different institutions, staff from different disciplines, as well as interaction with patients. We also need to channel our resources to address COVID-related issues, and that required the reduction of non-essential patient activities. Of course, that will include non-critical outpatient appointments as well as surgeries. Changi General Hospital, or in short CGH, is one of the 13 public hospitals in Singapore that manages COVID-suspected and positive patients. Management of breast cancer patients requires a delicate balance between achieving the best oncological outcomes while not increasing the risk of severe acute respiratory syndrome or SARS-CoV in this vulnerable group. There was a previous study in China where a nationwide analysis of cancer patients was conducted, and this study concluded that patients with cancer might have a higher risk of COVID-19 and poorer outcomes as well. So breast cancer, in fact, I think is the most common cancer not only amongst women in Singapore, but worldwide. The Division of Breast Surgery in CGH is a full-fledged tertiary referral center that delivers one-stop comprehensive care to residents living mainly in the east of Singapore. We have 4 full-time specialist breast surgeons and 2 full-time non-specialist doctors. In addition, we also have 6 external doctors from different institutions around the country who come to the center on a regular basis to provide outpatient consultations and be part of our multidisciplinary meetings. Our division is also an accredited assessment center for Breast Screen Singapore, and Breast Screen Singapore is a nationwide breast cancer screening program managed by the Health Promotion Board in Singapore. Furthermore, our doctors are also teaching faculty for 3 medical schools in Singapore, and we are also part of our surgical residency training program. Just to give a little bit of background on our workload, from the year 2015 to 2019, our total outpatient clinic visits number at approximately 30,000, and we have a relatively high operative volume of about 2,500 breast surgeries, including oncoplastic as well as reconstructive surgeries. So because of all this and because of COVID, we have to adapt. And what do we do to adapt in our clinical practice? First, I would like to discuss with all of you about our outpatient clinic visits adaptation. So as I've mentioned earlier, at the start of COVID in February 2020, Ministry of Health declared doors gone orange, and essentially it meant a certain degree of lockdown of healthcare staff to their own institutions. Cross-institutional activities were actually not allowed. As a result, as I mentioned earlier, we have 6 external doctors. They could not come to our hospital to provide outpatient consults. Our in-house doctors then had to take over the care of their patients, which led to a sudden increase in outpatient load for us. To cope with this surge, we reviewed the clinical records of these patients to determine their need for their clinic review. Those who are coming for routine follow-ups for benign conditions, their appointments will be postponed to a later date. Patients with abnormal investigation results or when otherwise on follow-up for breast cancer continued to be seen. Any such patients who did not attend their scheduled appointments will be contacted by our nurses and their appointments rescheduled. Should they then decline to come due to the fear of contracting COVID-19, their particulars will be recorded in a secure database in order for us to contact them once the situation improves. The nurses would also check if they had adequate medication. In order to cope with this sudden influx of patients who were not previously under our care, we actually reviewed their patients' records in our electronic health record system prior to their appointments to summarize all their issues. And this definitely helps to facilitate the simplest transfer of care from the external doctors to us. In addition, we're just worried should any of our doctors were to become unfit to work, either due to quarantine or due to exposure to COVID-19, another colleague can then fill in the gap with little compromise to patient care. In addition, our clinic resources of both our external doctors and ours were suspended to cope with the increasing load. This meant that existing appointments were actually maintained, but we don't add any additional appointment slots to that. However, as we are a tertiary referral center, appointment slots for urgent new referrals were not suspended, and these include cases of breast abscess, suspicious mammogram or ultrasound findings of BIRADS 4 or 5 categories, which means that potentially they can be suspicious, and any patients with suspicious signs or symptoms of breast cancer or newly diagnosed breast cancer will continue to be seen. The adjustment of our clinic resources were initially implemented from February to May 2020. Hence, all non-critical patients' appointments were postponed until June. However, when COVID-19 was declared as a pandemic and the situation worsened in Singapore, these clinic suspensions were then extended to December last year. This allowed us to cope with the postponed cases and also to prepare for the possibility of deployment of our staff to COVID-19 areas. So then that was from February to March. In April 2020, as the situation worsened, the Ministry of Health of Singapore announced the circuit breaker measures. And the circuit breaker measures essentially meant a certain degree of lockdown. And it included a set of essential face-to-face medical services that require certain changes, and these include cancer services, which when delayed will increase, of course, the chances of relapse or deterioration. Our outpatient load actually consists of patients with both cancer and non-cancer conditions. And the non-cancer patients that we kept are mainly those with high-risk lesions, strong family history, or breast imaging abnormalities. With the commencement of the circuit breaker measures, the Ministry of Health mandated that all non-essential patient visits to the hospitals to be postponed. To do this, we collated a list of all the patients coming in for consultations from April to June 2020. These patients' records and any recent investigation results were reviewed. So the following are the list of patients whose outpatient appointments were not to be postponed. Firstly, of course, patients with newly diagnosed breast cancer patients, or patients who are on routine follow-up within the first 2 years of their treatment, as the risk of recurrence within the first 2 years of treatment is higher. We will also continue seeing non-cancer patients, but with recent investigations results revealing abnormalities, and these abnormalities could be malignant. And of course, any patients with recent new onset of symptoms, we would not delay their diagnosis and treatment, hence we will continue seeing them. Our nurses would then contact patients again, and this is where I think a multidisciplinary team approach is very important, because we have a very good support system from our breast care nurses who would actually contact the patients to tell them that their appointments can be safely postponed and to make sure that they are not symptomatic and they have sufficient medication for those patients who are on endocrine therapy, for example. Any patient who was symptomatic during our nurses' contact would be advised to come for their original appointment. So within 3 days of looking through all the records, we actually looked through about 450 records and reduced the number of outpatient consultations to 24% of the original numbers. And this was subsequently done for the month of May and June as well. So this is a very simple table to summarize our principle for outpatient visits management. We try to minimize outpatient visits as much as possible, to replace it with telemedicine or teleconsult if appropriate, and priority are given to conditions that, when delayed, would increase the chances of relapse or deterioration. I would like to show and share some pictures of what we do in our outpatient clinic after COVID-19. So you can see here at our registration counter where my patient service associate or nurses register the patients and process their payments. We have this barrier here to actually protect them, and of course we make it as spacious as possible. We space out wherever we can. And this is our patient waiting area. As we can see here, so, the safe distancing, basically we space out the areas on the seats available, and of course, set constant reminder for our visitors or patients. So during these few crucial months where COVID-19 cases were on the rise, screening was deemed a non-essential medical services and was thus suspended when the circuit breaker was implemented. However, women who were recalled for abnormalities detected on their screening mammogram that was already performed continued to be reviewed by our breast radiologists, because we felt that evaluation of these ladies should not be delayed, as they do have a higher risk of malignancy in view of the abnormalities. So the attendance rate at our screening clinic were well maintained, with only about 10% of ladies calling in to postpone their appointments. And these were quickly filled by others who requested for earlier appointments. We feel that the ability to maintain healthy attendance rates amidst our limited resources again required great team multidisciplinary effort, in this case between the radiologists and surgeons. And this is to summarize our approach to screening and imaging. Try to minimize hospital visits as much as possible. We defer all screening imaging for at least 6 to 12 months, and we give priority to conditions that when delayed would again increase the chances of relapse or deterioration. So next, what about surgery cases? Our division of breast surgery is part of the Department of Surgery, and we do have other subspecialties in the department, such as upper gastrointestinal surgery, colorectal surgery, head and neck surgery, hepatobiliary surgery, vascular surgery, as well as plastic and reconstructive surgery. While vascular and plastic team have their own operating theatre list, the rest of the department share 3 operating theatre lists on a daily basis during the period of time. Before COVID-19, our division was allocated 2 operating theatre lists a week. And most of our surgeries are performed on a day surgery or 23-hour ward, that means a one overnight stay basis. And this applied to therapeutic breast cancer surgeries, including higher level surgeries such as oncoplastic and reconstructive surgeries. Patients who require longer stay, for example, are those patients who underwent a free flap or autologous flap reconstruction such as TRAM or DIAP flap. And our day surgery and 23-hour wards are both located in a separate facility from our inpatient wards. We think that this is definitely good in the context of COVID-19 because this practice actually limits the exposure of our patients and clinicians to the general hospital cohort. So when DORSCON Orange was announced in February 2020, of course, that led to a reduction of resources, and that included staff, especially nursing staff and anesthetists running the operating theatres because they are deployed to COVID-19 areas. So this is when the hospital implemented a cohort-based OT booking system for elective surgeries. That means the whole Department of Surgery will share 1 operating theatre on 3 days and 2 operating theatres on 2 days per week. This actually resulted in the reduction of OT allocations for the division of breast surgery to just 1 full operating theatre list per week. So then we decided that all benign, non-urgent diagnostic breast surgeries were postponed indefinitely, but patient details were recorded in a secure database so that we can contact them to reschedule their operation when the situation permits. The priority during this period of time was thus given to oncological cases or cases that were deemed indeterminate and required diagnostic surgery. We still offered immediate reconstruction options such as autologous or implants and oncoplastic surgery where the operating theatre list is available and where we think that the time taken for the operation is still within acceptable period. So unfortunately, by March 2020, our wait time for breast cancer surgery was beyond 6 weeks. And this was unacceptable to us, so we appealed for more operating theatre lists and that was successful, leading to an increase in theatre lists to 2 per week for the division of breast surgery. With that, we were able to reduce the wait time to about 3 weeks. So then again come April, as the situation worsens, there are more deployment of staff to COVID-related areas, and this led to further reduction in our operating theatre list. But the good thing and the blessing in disguise is that because of COVID as well, there's a reduction in the number of clinic attendance and outpatient clinic visits. We have a concurrent reduction in newly diagnosed breast cancer case. Hence, the operative wait time for cancer patients was not any longer than before. So on top of that, with regards to surgery, we actually had team segregation. So in our division, we segregated our staff into 2 surgical teams, and each team consisted of 3 doctors, a senior specialist surgeon, a junior specialist surgeon, and a non-specialist doctors. And we confined ourselves strictly to our teams when performing surgery, and this was because during the surgery, it is impossible to maintain a safe distancing of 1 meter between the staff and patient. In addition, because studies have shown that aerosolization of the SARS-CoV-2 virus has been reported when energy devices such as diatomy pens are used. Hence, we're worried should the patient subsequently be diagnosed with COVID-19, only the surgical team who were involved in the same operation needs to be quarantined. the rest of the team or the other team would still be able to run the service and will not compromise on patients' care. Likewise, we conduct our inpatient ward rounds and outpatient clinics in a similar manner. So we also reviewed the nature of operations that we conducted. Therapeutic surgery for breast cancer and diagnostic surgery for suspicious lesions continued, but they're all performed by the most experienced breast surgeon in each team. Newly diagnosed breast cancer patients who then opted for immediate breast reconstruction post-mastectomy with the TREM or DIEP flap were advised to have expander implant inserted instead, with subsequent definitive reconstruction. This was done to shorten the operative time, the length of inpatient stay, and of course to reduce complication risk. So as per hospital guidelines, surgery for suspected or confirmed COVID-19 cases are performed under full personal protective equipment and powered air purifying respirator respectively. This is a summary of our approach for surgery during this period. We only perform surgery for urgent or life-threatening conditions. Oncologic resection achieved with the shortest anesthesia, the least mobility, the shortest hospital stay, and fastest recovery will be chosen. And of course, in certain cases, we consider alternatives to surgery. This is a simple sharing from myself. This is the number of oncological resections that I've performed over the past 1.5 years. You can see that this has not differed a lot from the pre-COVID times for myself, and it is because of all this arrangement and a multidisciplinary team effort from everyone from my team that were able to achieve good oncological care for our patients with breast cancer. Next, we'll move on to systemic treatment and radiation. So breast cancer patients, some of them will require systemic therapy or radiation after their surgery, and these recommendations were made at our multidisciplinary meeting. These meetings continued during this period because we do not want to compromise patient care, but we make sure only essential staff needed to make crucial management decisions are present, and when the circuit breaker measures were implemented, we switched all our meetings to virtual via teleconferencing. And these measures were all taken as part of a multidisciplinary effort in order to ensure timely delivery of care for our breast cancer patients while we keep to our safe distancing safety measures. So for patients who require systemic or radiation therapy, we were mindful to ensure safe distancing, we minimize immunosuppression, and reduce unnecessary visits. So we have to suspend all other non-clinical activities during this period. For example, education, whether it's continued medical education for our staff, undergraduate students, or postgraduate students. So all non-essential academic meetings were cancelled to minimize contact between staff, and our journal ratings or journal club were conducted online with sharing of interesting journal articles. During this period of time, formal lectures and bedside tutorials were suspended as well. And for students, all elective attachments were cancelled. All our medical and nursing schools affiliated to our institution suspended their clinical attachment during this period of time and replaced with home-based online learning. All this for the same reason, to minimize exposure to potential COVID-19 patients. Clinical research for this period of time were also suspended. And for breast cancer, we used to hold support group events for our survivors and volunteer training programs, but they were all put on hold during this crucial period of time. Patients continued to have standard counseling by our doctors and breast care nurses on a one-to-one basis as well. So we believe that during this period of time, despite our best efforts, there will be certain impact on patients. The magnitude of the long-term implications due to the reduction in clinical activities is currently still unknown. But we have noticed that patients who have either deferred or failed to attend their hospital appointments have increased during this period of time and actually ever since then. And this is due to the fear of contracting getting COVID-19 in a hospital. However, we believe that there is a chance that all these postponements may lead to a delay in diagnosis and treatment. So for undetected malignancy, this delay in diagnosis and treatment might inevitably lead to unfavorable long-term outcomes. So as the number of COVID-19 cases increases, we believe that more resources will be channeled towards the areas in need. And we're very lucky that despite all this, we're able to keep our wait time to therapeutic cancer surgery to about 4 weeks. However, patients opted for longer surgery, such as a free autologous flap reconstruction, will have to undergo stage surgery with all our recommendations. And this will of course incur higher total treatment costs, as well as having to undergo another general anesthesia, along with its inherent risk. And of course, the cosmetic outcomes also may not be as ideal as immediate reconstruction. When we suspend patient support activities, there may be a certain degree of psychological impact on their patients and families that may not be immediately apparent. And without these services and activities, patients as well as their families lose an avenue to share their concerns and worries. They may also feel alone in their cancer treatment journey and may be deprived of coping techniques to deal with the stress. And similarly, the caregivers can also develop caregiver stress that is not addressed, may lead to adverse psychological outcomes. So we feel that COVID-19 has taught us a lot of things, and while managing our breast cancer patients, while making sure that their care is not compromised, we do learn. So most importantly, we learned that multidisciplinary efforts from important stakeholders in breast cancer care is very important. And I cannot emphasize more on this. And this includes, but not limited to, surgeons like myself, our radiologist colleague, medical oncologists, radiation oncologists, pathologists, and our breast care nurses. And I really believe and feel that it requires a concerted effort from all of us to ensure timely delivery of standard of care in this new normal. So I would like to share the other paper that my team and myself have published last year as well. And this is what we call as a prioritization aid to help others who may be in the same situation as us in order to maximize and optimize patients' care. So we prioritize for outpatient visits scenarios that we advise not to be postponed or conditions that we feel can be postponed. So I wouldn't go into the details of it as I believe that all of you can read up on this article during your free time. But essentially, we keep anything that is urgent, patients that are symptomatic on our list, while the rest are postponed. We also prioritize the management of breast cancer, and this we stratified it according to the DORSCON level as well as resource availability. Essentially, the principles are similar to what I've explained earlier. However, in terms of resources, if it is limited, we actually stratify the patients further according to their priority, whether they're high, medium, or low, and we make our recommendations to either keep or postpone their appointments. So for surgery, as I mentioned earlier, we do not exclude all reconstructive surgeries as long as the surgeries can be done in a timely manner within an acceptable time frame. We still allow the reconstruction to take place. And for systemic treatment and radiation therapy, if patients need it, they will still go for it, but we try to minimize drugs or chemo drugs that are extremely immunosuppressive in order to manage patients better during this period. And so, what are our updates since last year? As I put it here, I think virtual is the keyword. Virtual is the future now. Why I say so is because everything can be done virtually online now, and I feel that that is what COVID-19 has taught us. Everything from our multidisciplinary team meeting to our education, whether it's for doctors, trainees, or nurses, even our breast cancer patient support group are done virtually and online now. And we have since started telemedicine in the form of phone consultation as well as video consultation for some of our follow-up patients. In clinical practice, we have tried a lot of new technology and equipments to actually reduce operating theatre time or to decouple the surgery and radiology schedule. And I think all this can't be done without a concerted multidisciplinary team effort. So for this, I'm very thankful to everybody in my division and all the specialists and the support staff that have worked together with us to provide optimal and timely care for our breast cancer patients. And with that, thank all of you for listening in to me today. And meanwhile, I hope everyone will stay safe and healthy. Last but not the least, hopefully when the borders are open, I hope to see you guys in Singapore. Thank you very much.
Next up, we have a speaker from Japan. He's currently in the Schematics Incorporation. His name is Dr. Howari Sabirin, originally from Indonesia. And also, similar to Dr. Tao, he's actually working also on the AI, artificial intelligence, but his major is actually to work on the development of software solutions based on computer vision and image processing for agricultural theme automation, such as weed detection, crops detection, and etc. So today he's going to share with us how to use artificial intelligence for integrative agricultural work comfort. So let's welcome Dr. Howari.
Hello everyone, my name is Howari Sabirin. I'm a researcher from Schematics Corporation in Japan. So this time I would like to have a presentation. The title is AI for Smart Agriculture Work Comfort. So this talk is an invited talk by my colleagues in KAIST, Ms. Sao PR. So she invited me to give some brief presentation for the bio integration paper talk. So this time I would like to explain to you about my current research work, especially related to the smart agriculture work. So this topic is actually will be a little bit broad in the sense of that I'm not sure how high or how low the level of audience. So I will briefly talk first related to the introduction of the digital image processing itself. So maybe many of you is already expert in this topic, but I hope if there are many also students that will see this presentation, they will also get some insight related to the basics of the digital image processing. And then after that, I will continue with brief introductions to the AI-based image processing, especially related to how the object is segmented and detected, especially for the purpose of the agriculture applications. That's why in the last part of this presentation, I will introduce some smart agriculture applications that we are currently working on in Schematics. So basically, Schematics is a company that is working on processing and managing the image taken by aerial drones, such as for the farmers, for farm and for the fields, such that the farmers can somehow manage to control or to manage their farms easily. by looking at the data and the processed information that is taken by the camera. So I would like to start with brief introductions to digital image processing. So I will not be long in this part. So I hope most of you are already familiar with image, especially digital image. So what is digital image? So it's basically an image that structured digitally as group of picture elements, or we call pixels, where each pixels may contain various information. So if you see the picture at the right side of this page, this is actually two images that are composite into one, where it makes some effect that there seems two persons at the same image, but actually these two images taken by the same persons. So these are the two same persons, showing that a digital image is very easy to be manipulated. And this is because we are looking at the informations that is contains in their pixels. So what is actually a pixels? So if you see this area on the right side, this is taken from this area between the background, the wall, and the hand part of this person. So we can see that each there is a blocks here. This is what we call the pixels, and each of them contains the information regarding the colors on this image. And this color information can be represented by the main colors, red, green, and blue, and the combinations of three of them. So, and we can also represent those information as hue and saturations information, which is the colors that is determined by the light spectrum, and its saturation on how bold or how faint is the color intensity. And then we can also represent each pixels as the luminance intensity, the brightness, how bright is color at certain pixels. Beside color information, if you can see here that we can see that there is a difference between the background, the wall, and the red colors of this sweatshirt. So by looking at the difference of the colors between the background and the foreground, then we can determine the age of this object. And furthermore, we can then determine the segment between the background and the foreground, and then we can also determine the texture and so on and so forth. So based on this kind of information in each pixels, then we can do many things in digital image. So yeah, this is basically how to manage and process the pixels in the digital image processing. So it's basically comprises of image analysis, how the image is obtained and pre-processed, and how the image is can be processed to get the recognitions of contents inside each image, like object recognition or segmentation and so on and so forth. And also how to manage the amount of data inside the image itself. So basically, this kind of process are what we are doing in the image processing. I will not going too far with that. So this is basics on how to obtain a digital image. So it's basically similar to how our eyes can see an object. So it's basically when a source of light comes to an object, then its reflections is captured by imaging system, whether it's a lens and the filters, and then it comes to the image sensors. And this image sensor has area represented by blocks here, which also basically representing picture elements or pixels, where each component of light that is reflected by the objects is coming. And each area of this sensor will take how much the level of intensity for each of these components, such that it can represent the real objects. So based on that, we can model a digital image as a light intensity function, which is in 2 dimensions, the height and the width. And each function is quantized into 8 bits to determine the level of the intensity. So, for example, if we have a green area here, let's say this is 1 pixels, this one. So, green color is represented by 3 channels, red, green, and blue, and each channel has 8 bits value that represent the quantized intensity level. So, for example, if we have a green pixel here, then it's obvious that the green components of this pixel has the highest value, let's say 249, and the remaining components, red and blue, has lower level. So, for example, if we have these pixels of the sky, then we would have a higher light intensity in the blue channel and lower in the red and green channels. So based on that information, then we can combine, or we can determine the intensity level of each channels, and then we can recognize what kind of colors that are in the image. And we can also process the image based on the difference of intensity in that image. So for example, if we have this kind of image, maybe some kind of flower here, this one is pink and this one is red. So we can easily know that this pixels has more intensity of red, as you can see here. So it's the brightest area of the red component, but at the same time it has darker or lower intensity of green and blue channel. So based on this information, then we can further process the image to determine what kind of information that we want to take and we want to discard. So now I will go to the introduction of the AI-based image processing itself. But for that, we can start from the simple task related to the object detection. So it's basically we want to find and we want to determine the point of interest in an image. So the problem is that what is the point of interest that we want to find and how to find it. So for example, if we have this kind of image, there are trees here, there are flowers, boxes, stairs, green area, sky, mountain, house. So what is our point of interest? So based on this, first we usually need to determine exactly what we want to find. Otherwise, it might be too complex for the system to determine or to determine the point of interest as all objects in this image. That's why in the topics of object detection, usually we localize or we limit our problem to determine certain point of interest. Let's say our point of interest in this image is this tree, this one. The next question would be how to find this tree. So to find this tree, then we need to also know what is the feature in terms of maybe what we see from this image. If we want to find the tree, then we might need to know how its color, how its shape, maybe also its size, its position, and so on and so forth. So based on that information, then finally we can find the tree. So these two problems is actually what we want the machine to learn, and then we can ask it as the system to determine the locations of that object in the image. In simplest way, we usually start by performing color analysis, where here we determine the most suitable color scheme for object detection. In this part, we usually working with how to determine the intensity of luminance or brightness of each pixels, how strong is the color, the saturation level, and also we might need to know how the structure of colors in such image, such that we want to know their comparisons or their ratio. So for example, if we look at this certain image, we have the image of house on the foreground and the mountain in the background. So if we see at the main color scheme, main color means the main colors of red, green, and blue, we can see that it might be difficult to determine. Let's say we want to find a house here. It might be difficult to check only the red or green or blue information from this image. Then we can also find another color scheme based on the light intensity. So for example, let's see this HSV or HLS color scheme. So these color schemes split the image into three parts. The first one is the hue, which is the visible light spectrum. From the lowest is purple, and the highest, the longest frequency is red. And then S is the saturation, how strong or how fade is the colors. And V or L in this color scheme is how high or how low the brightness intensity. So based on this information, then if you can see the difference between the RGB scheme here and the HSV or HLS scheme here, if you want to find the house where it's difficult to find certain area in R or G or B channels, we can see that in hue channels, we can almost see the difference of the color light spectrum between the house and the other area of this of the area in this image. So based on this information, then we can say that if we use this HSV or HLS color information, then we can segment or we can obtain the house area by checking at the pixels where the hue or the color spectrum is in a certain value like this one. This is more easily recognizable compared to RGB. So the other way, especially related to the agriculture image, we are using what we call vegetation index. So it's basically determine the shade of green, and it's called NGRDI, normalized difference green and red, normalized green red difference index. So it's basically calculating how much strong is green value or green pixels in an image, because most of the colors in agriculture, especially related to the leaves of crops or plants, are green. So we can use this information to localize the area of the pixels of leaves and the other area. And the next is the texture analysis. Here we observe spatial relations between two or more pixels, especially the neighboring pixels. So from that information, we can get the edges, corners, patterns, contours, and so on and so forth. So for example, if we see this image, then we can see the difference between the pixels of the background and the foreground, and then we can get the edge of this certain animal. And then based on those informations, color information, texture information, and how we select which color scheme is the best one for our cases, then we can feed that information to a machine learning system. Because machine learning is actually how we give correct information to the system and let the system process it such that it can learn what is the feature of the certain object that we give to that system. So for example, this is similar to how we understand certain objects. So maybe when we are when we are small, when we are children, our teachers give us information regarding an apple, what its color and shape and so on and so forth. And then by time goes by, we learn apple can be in many shape and conditions and other colors. And based on this kind of information, then we can finally knows any kind of apples if we see an apple. So it's similar to machine learning. Human usually define the features of the object, especially different colors, texture, and so on and so forth. And then the system continue to learn the features to differentiate that objects from other objects that is not defined. So yes, it's basically a certain repetition of loop and conditions examination. So previously we talked about Apple. So now let's see an example here. We want to teach the system how it can recognize a cat from dog. So basically we teach the system by a lot of image of cats and dogs, and then the system will iteratively calculate the features of cats or dog. And then when a different image of cat, for example, is given to the system, then it will predict and it will calculate the difference between the features of cats that the system already learned compared to the new image of cat, and then it will get how much difference, or in other words, how much the error between the feature that the system already learned compared to the new image. Then it will predict whether it's the correct system or whether it's correct image of cat or other. So similarly, for the finding the information of, let's say here we have a certain kind of crops. What we do is we collect many image of fields and we collect it as training data. So this training data is kind of annotated information from the image. So let's say we have this kind of farm image, and then we need to manually annotate, or we give some information in this image specifying that this area is the actual objects that we want the system to learn. For example, the color should be green and the shape should be small like this one. And we feed this kind of information to the system many times until it learns by itself. And finally, it can learn what is the feature of the plants or the crop that we want the system to learn. So for this method, sometimes we not need to develop our own. Instead, we can use existing scheme like mass Cartesian, YOLO, or unit, something like that. So it's basically some kind of a scheme in machine learning that we can use to fit the systems so it can learn how to recognize such objects. And then finally, we do a segmentation process, whether it can be what we call semantic segmentation or instance segmentation. So semantic segmentation, that means that we want to differentiate this image as different types of area and objects. Or for example, here, we can segment these objects by different kind of object types like sky, road, or background, and so on and so forth. But in instance segmentation, not only we differentiate the types of objects we segment, we want to also to recognize each segmented area as different objects. So again, we can obtain such segmentation by observing the texture, the colors, and other information from the pixels in the training data. So which one is the best? So it depends on the image condition and expected output, whether the quality is good or bad, or the types of object to be found is dense or sparse, or has, or it's clear or salient, or its shape is good or bad, and so on and so forth. And we also need to consider that the training data is sufficient for us to fit the machine so it can learn, and whether the device to perform the machine learning is good, or maybe the expected output of our system is not too complex. So maybe simple results may not require a complex process. So now this is the last part, is the agricultural applications that we are currently working on. So basically the purposes are to ease the physical activities of farmers and to provide the decision support system for the farmers and to improve harvest quality and quantity. So first, I would like to introduce the crop detection from drone image like this one. Here we have an image from the drone, and which already composite from drones that are flying throughout this field. So the next step, we segment the plants from the soil. And finally, we can detect, although maybe not 100%, but most of the plants can be detected, like this one. And furthermore, we can also conduct further process to predict how many leaves are present in this crop. The next is the web-based cabbage quality management. This is our product actually. You can check here, but it's in Japanese. But anyway, so this is basically an example of how we feed many image of cabbage to the system, because the shape and the color of cabbage is certainly similar. And based on this information, then we can predict the size of each cabbage and its quality. The next is paddy field weed detection. So here we can use NGRDI at first to distinguish the weeds and rice leaves. As you can see here, the green area is the detected rice leaves, and the red colors are the detected weeds. So basically, from this image, the farmers can easily find the area in his field where the pesticide or insecticide should be applied to this farm. Next is also we can work with small objects like seed analysis, where we can use texture and color analysis on the detected segment. So for example, we can detect the quality of the seed of rice here, whether it's good, that means it produces some kind of leaves, and whether it's bad, which is it does not produce some leaves. And also we can do many things such as detecting this kind of weeds, seeds in larger grids of farm, and then check how much leaves the seeds actually produce. And then we can categorize it, whether it's good or bad. And the next is also we are working with rice grain detection. This is also our product. You can check here. It's a smartphone-based product. Well, it's currently in Japanese, but basically what we do is we get image from camera of rice in kind of dish, and then we perform segmentation for each grains, and then from that we can calculate how many grains are in this dish and what is the condition of each rice. Of course, there are many more possible application in agricultural applications by utilizing the AI or image processing. We can detect and track livestock, because we can segment each livestock and each types if we have enough data to be trained. We can detect the quality of flowers, whether it's bloom or withered. We can predict land quality by the color of the soil. We can detect and classify pests in certain plant. Also, we can predict the strength of water in a stream for irrigation, for example. Let's say we put some object and then we capture the video of that object running in the stream, then we can predict the speed. And then we can do some kind of count and predict the amount of seeds of fish in a stream or shrimp in a farm. Like we can determine how many seeds of fish, and we can determine how much food it needs for this amount of fish. And also we can do farm nighttime surveillance using infrared camera and so on and so forth. So basically, by analyzing texture, colors, and other information in the pixels, we can do a lot of things. Not only, of course, in agriculture, but in other works. But basically, in agriculture, then we have many possible potential applications that we can use to improve the work of farmers in the field, especially when the amount of area that needs to be handled by farmers getting larger, but the workers is getting lower amount of workers, then we hope that this kind of agricultural applications can help improve and ease the work conditions of agricultural workers. So thank you for your attentions. If you have any questions, comments, please contact Ms. So PR, and later she can contact me to get your questions and comments. I'd be happy to receive them from you. Okay, thank you very much once again, and I hope this presentation is fruitful, and have a nice meetings. Thank you very much.
Last but not least, we have also our editorial board member, Dr. Chun Jae Tan from University of Science Malaysia, who he is currently serving as a senior lecturer there. And his major is actually doing tissue engineering and regenerative medicine. So, and today he's going to talk a little bit about his current work with the title Road to Cardiac Regeneration. So let's welcome him.
Hi, thank you very much to the organizing committee for inviting me to share these lectures. My name is Tan Junji. I'm from Malaysia. I'm currently an associate professor in Advanced Medical and Dental Institute, University of Science Malaysia. Today, I would like to share with you my experience in cardiac regeneration. I have been with the field for more than 10 years. I have dealt with adult stem cells to pluripotent stem cells, and we have moved from sending cells to our heart, the injured heart, trying to see the therapeutic effects, to doing more of the differentiations and also tissue engineering. And today I would like to share with you what we have done so far and what we are looking forward to in the field of heart regenerations. So today we are going to touch on four main topics. We are going to discuss why do we need to do heart regeneration, what's the rationale of the whole idea, and how we actually address the limitation in the current therapies. And what are the early attempts in doing the heart regenerations, as in like what are the heart cells, stem cells that we actually use, or people has already studied in the past in the clinics or in the preclinical settings. And the third, we are going to discuss about how has the cardiac regenerative research has evolved from bench to bedside, and what are the current advances in the field that actually put us more closest to clinical applications. The fourth and the last will be the things that we can actually look for, what's the road ahead for cardiac regenerations, especially in the advances in cells, differentiations, and also tissue engineering. So we are going to start with the first rationales and also the limitations. So looking back at the disease prevalence, and cardiovascular disease is still the main cause of death or worldwide. Is still costing about 17.8 million people's life. And if we actually focus on the four countries and also the European Unions, Americas and China, comparing with Malaysia's, we can actually see the mortality rate is still very high. 1 in every 4 Americans actually die of cardiovascular disease. And China is not doing any better. And European Union, 37.1% of them actually die of cardiovascular disease. And in Malaysia, we are not any better as well. We have 15, and it's still the primary cause of death here in my country. So if you actually look at the economic burdens with the data that I can actually gather from all the published papers, is costing quite a lot to each and every single countries, and it really depends on. This is not a kind of comparable figures, but it really depends on the density of the populations and also the GDPs and also the cost of livings. But what we are trying to say over here is that the current burdens of cardiovascular disease, although it has actually improved over time with the technology, with the advances in drug approach, it's still costing a lot. People are still living with heart failure, and they have a relatively poor quality of life. So it all begins with coronary artery disease and myocardial infarctions, where when you have a coronary artery that actually serves the main artery that actually serves the myocardium, the heart tissues, when you have a blockade in it, you will start to suffer ischemia, where you have cardiomyocytes starting to die, and over time, these dead cardiomyocytes will be replaced with some fibrosis. You get more necrotic tissue forming in the heart, and ultimately it will remodel to become a much larger chamber with a weaker contractility. So this is what we call heart remodeling, where we're trying to actually reverse this or stop this progress, as it's kind of like irreversible when you actually get up to the end stage. So when you have heart failure, um, on the left, you can actually see this is the very nice normal human heart, where you get ejection fractions of more than 70%. These are cine images that I've obtained from the Oxford Center of Magnetic Resonance. And on the right, you can actually see for the left ventricular infarcts, there are the regions of the heart that's not contracting, that's a very akinetic, and the chamber itself is quite large, and the ejection fraction is about 49%. The ejection fraction means the blood that the heart are able to pump, the fractions of blood are able to pump out of the heart. So looking back at the survival rate of heart failures, and from the day of diagnosis, after 1 year, only 75.9% of them survive. And every 5 years, you actually reduce the survival rate by half. So after 5 years, you get only 45.5% of them survive. 10 years later, you get 24.5%, and 15 years you only have 12.7% of them manage to live that long. So the heart, when they actually get up to the stage where it's completely remodeled, there's nothing we can do except heart transplantations. And this is the only treatments we are able to offer after all the available therapies in the clinics. You give drugs, you give surgery, you do whatever you could to help the heart to pump again. But ultimately, it actually fails. The heart function will just deteriorate every year over time. And the only way to save the heart failure patient is by doing heart transplantations. But donor is not always available, as we know, and we also have a problem with the compatibilities. Even though you get the donors, there's a list of people, recipients, they're waiting for the compatible hearts, and it also depends on the severity. So it's not some of the off-the-shelf solutions that we are able to offer to those people with heart failure. So what are the early attempts? That's why we started to actually look into the alternatives, whether those are dead myocytes, since they cannot grow by itself in the adulthood, whether we can replenish them by sending some of the stem cells that are able to differentiate and make heart cells. And what are those cells that we have at hand to do this? So there are types of stem cells that people already explore. The one in pink are the first generation stem cell that we already put into clinical trials that have been tested. We also have come to the conclusions what are the limitations of those cells. And then we actually move into the second generation of stem cells, where they are more likely to form heart cells. And that's the ultimate aim of heart regeneration, is to regrow the heart cells. So in the early days, about 10 years ago, more than 10 years already, people have started to actually send gliomyoblasts, bone marrow mononuclear cells or MSCs into our heart, and trying to actually make them and to grow heart cells. They have seen some of the promising improvement in heart function in animals, but unfortunately, the outcome is quite depressing. And I'm going to actually explain a little bit more on those cells in the later slide. But here I'm going to introduce to you that there are a few generations of cell therapy right now. The first generation is basically overs, and we are now looking into more cardiac poietic stem cells, which is more like cardiac progenitors, inducible stem cells, and brain stem cells. So these are the first generation and second generation cell therapy that has been put to clinical trials. You have seen there are lots of clinical trials. I'm sure they are not just this. I think there are more that we could actually summarize. I actually published the data back in 2007. So we have done lots on the first generation, and we are still looking forward to see what is coming out in the second generation. Is more into on a cardiac differentiation potential cells that are able to actually differentiate into cardiomyocytes. So, like I said, the outcome from the first generation's clinical trials were quite depressing. So it's quite disappointing. Some of that bone marrow mononuclear cells, there are so many clinical trials that have been conducted. We get very limited improvement or regenerations. Even they are significant, they are very marginal. So we don't see much of a differentiated cells. Even in the preclinical setting, when we actually send bone marrow mononuclear cells in, we don't see new heart cells formations. And we also have a problem with post-transplantations and engraftment, where we actually send some of the cells through intracoronary injections. We do get a lot of how to say losses of the cells number because of the force that's exerted by the heart that actually force the cells out from the heart itself. So, so these are 4 limitations. Right now we are seeing MSCs. Lots of people are still working on MSCs. This is one of the promising cells that could actually be able to offer some of the cardiac functions, but up to this stage, when I actually dealt with mesenchymal stem cell, regardless of what small molecules or differentiation would be actually put to the cells, we hardly see them becoming a functional cardiomyocyte. They may express some of the cardiac markers, they may upregulate some of the cardiac-related or specific genes, but that doesn't mean that they can become a functional beating cardiomyocyte at the end. So this is some of the hurdles we have with the first generation cell types. So for second generation, now we are just focusing on the adult stem cell, means the cardiac progenitor cells or cardiosphere-derived cells. Those 2 cells have been has been tested in the clinical trials. I won't actually touch too much on the CK cardiac progenitor cells because of the case with pure emphasis. They actually cast more of the doubt on the cells and the capabilities to regenerate the heart. But generally, from all the adult stem cells that we have dealt, we have problem with the yield where you can actually get the cells from the biopsies. We have to grow them for at least a month to get sufficient cell therapeutically relevant cell numbers for injections. And they are able to become cardiomyocyte. Like I said, they can express some of the markers, but whether they are functional or not is still in hot debate. Transplantation issues, we can improve it by doing endocardial or epicardially injections. So it's intramyocardial injections where you get more retentions. But again, studies have shown that even if you actually do intramyocardial injection, you actually lose the cells over time. And whether they actually survive and then grow up to do what they need to or what they were expected to, it's still not there. I think that there are some of the research actually shows that if you actually do repeated doses, then it will actually increase the survival and also the engraftment. But whether this is something that is clinically applicable, it is still remains to be answered. But nevertheless, those cells actually show improved cardiac functions. So for I think the consensus in the field on adult cell therapy, the primary mechanism to explain the functional benefit that we have observed from all the animal study or clinical trials is the paracrine effects. Those effects, those secretums, including paracrine factors or extracellular vesicles or exosomes, they actually be able to confer certain protections to the cardiomyocyte, neighboring cardiomyocytes, to withstand the hostile ischemic conditions. And those protections actually make them to survive and keep up with the insult. So this actually makes more of the myocytes survive the ischemia, and so you have less fibrosis. You still have some contractile units that you need for the host to actually keep up with the cardiac output, and you have in some of the cells or the effect that they make more of the vascular that actually supply more nutrient or oxygen um, to the infarct region, and that actually prevents cardiac remodeling. Um, so we almost come to the dead end where which cells actually go for. We hardly actually see any of the new cardiomyocytes actually form from all the adult stem cells, or maybe to a minimal region on top of some of the limitations. What we quite uh, not until we have um, the Nobel laureates from Japan who actually introduced the technology of reprogramming and the generation of the induced pluripotent stem cell. So induced pluripotent stem cell is a technology where you insert 4 or 5 pluripotent genes into any of the somatic adult differentiated cells, and that will actually reprogram or revert the cells back to its pluripotent stage. And these pluripotent cells have a similar properties like embryonic stem cells, and they are able to derive to cardiomyocytes, neurons, pancreatic beta cell, hematopoietin, all type of stem cells you can name it in the body. And this actually solve problems that we encountered earlier with embryonic stem cells, especially on the ethical concern whether harvesting embryonic stem cells from a fertilized human egg is a form of homicide, and whether we can actually do it in a large scale. And on top of that, we also have seen um, um, the embryonic stem cell are definitely the allogenic source. There's no way you can actually get, uh, uh, or very rare, you get autologous from embryonic stem cells and pluripotent stem cell, induced pluripotent stem cells. You can basically get it from your own cells, and you can actually reprogram them and send them back to you if you need it. So reprogramming is more into like reversing the somatic cells back to the pluripotent stage and regain the plasticity similar to embryonic stem cells. And once the cell reach the pluripotent stage, we can actually roll it back down like the rolling back marbles down to the valleys with the signal that we actually induce them to direct him to the destination that we want. So the process of doing directed differentiation will actually enable us to produce the differentiated cells that we want from pluripotent stage, and that actually opens up lots of opportunities to create or generate cells that are unable to protein at this stage using any of the adult stem cells, including cardiomyocytes. So directed differentiations requires a developmental signaling map where certain temporal adjustment or stimulations of the pluripotent cells with a certain signal that is required during the development. When we actually apply the same on the dish, these cells can actually respond accordingly and become the cells that we want. And we pretty much have the map, signaling map of differentiation established. So making human cardiomyocytes is no longer a challenge now. That the real challenge is more to the cell type that we actually differentiate, because they are pluripotent cells. And if you actually differentiate it, you'll certainly get some of the non-cardiomyocyte cells that form together with the cardiomyocyte that we actually make them. Whether the cell's maturity is there, or when we have the cardiomyocyte, how we should actually deliver the cells to the heart. That's still very hostile ischemia, whether they can actually survive in ischemic hearts, and whether they integrate into the host myocardium and actually contributes to the function at the end. So all these are still remain to be tested. But in 2018, there were very landmark papers where Chuck Murray actually initiated this study in macaque, where he actually differentiated the embryonic stem cell derived cardiomyocytes, and they actually do it in the primates, the macaque. And he actually saw a lot of cardiomyocytes that are able to integrate into the myocardium. You can actually see on the figures the green human cardiomyocyte actually constitutes the whole myocardium extensively. That's impressive. And you can also see the therapy, the engrafted myocardium actually keep up with the muscle load. So we actually preserve the heart from getting the heart wall from getting thinner and mimicking a failing going towards failing phenotypes. So although I think from that study he also shows that you have quite extensive regeneration over here using iPS cells. You'll certainly be able to achieve the same in human. However, there are some of the hurdles, some of the problems we need to resolve is that there are some of the impurities during each of the differentiation. We know that a majority of the cells will become heart cells, but for some of the cells, they are not completely belongs to the ventricle. For example, the pacemaker cells. So because of some of the minor pacemaker cells that actually present in the population that they send in, they actually trigger ectopic electricity, and that actually creates the problems of arrhythmias in the heart, where you get another electricity source that's not supposed to be there in the ventricle. So now we want to actually also remove all the cardiomyocytes that's not ventricles, uh, um, uh, including the atrial cardiomyocytes completely from the dish. So we want to actually define, we actually did more of the chamber-specific cardiomyocyte differentiations. We make sure the cells that we are differentiating are ventricular, if you are sending to the ventricle, and we also look into strategies to remove all these sinoatrial cells, nodal cells, to make sure we actually minimize or completely eradicate these pacemaking cells from the cultures, and so we are able to safely deliver cells to the myocardium. So how has the cardiac regeneration evolved? So we have ongoing some clinical trials for cardiac tissue engineering. We Uh, People have done epicardial infarct repair using matrix or some of the cells embedded in the fibrin patch or hydrogels or collagens matrix with the bone marrow cells in order to have more like engraftment and also um, tapping on the paracrine effects of those cells to improve the heart function, if not regenerations. And having said that, when we have all the cardiomyocyte that we are able to produce, we will also bump into another problems during the process where after the differentiation, we actually find most of these cells, especially the induced pluripotent stem cell derived cardiomyocyte, they are relatively uh, premature. They are more like a fetal cardiomyocyte. How the two differs and why does it matters? It matters because they are not completely or maturely in terms of their structures and their strength. Because they are relatively small, the sarcomeres are not completely aligned. As you can see, this is one of the marine cardiomyocytes from postnatal 6 days to postnatal 20 days. You can see the massive changes in the cardiomyocyte structures and also some of the functions. Um, Mitochondria, valve, T tubules, whichever actually help the heart cells to actually function much better to deliver more of the strain, the contractility that is supposed to is not currently present in the iPS-derived myocyte. So the key to successful heart regeneration is still lies with cardiomyocyte maturation, regardless whether we want ultimately send the cells in a mature stage to the heart, or we need a mixture, or what stage of the cardiomyocyte we want to send for therapy. It remains to be explored, simply because we also want some of the cells, cardiomyocytes, are still able to proliferate, to regenerate the heart after the transplantations, or whether the mature cardiomyocyte can withstand the hostile environment in the infarct region, so that they can actually do the work, to reconstitute your heart and contribute to the contractility at the end. But having those informations to actually drive the cardiac maturation is key, and so that we know how to actually make them to mature, or what stage. We have a choice of choosing what stage of cells we want to actually send in. So the four key elements in cardiac maturation: the myofibril maturation, the electrophysiology functions in the cardiomyocyte, the metabolism shifting from glycolysis to more of the fatty acid oxidations, and increased electron transport change activity is more of the key to actually access more of the energy productions and also the contractility. The structures and the size that actually enable and confer the myocytes more of the force and strength that actually come with the maturity of the cells. And those four elements are very important to actually define whether the cardiomyocyte is matured or not. And we have already some of the strategies to drive the maturations. Either you actually do it more longer in the dish, which is quite random. It can actually go up to a year. We have grown cardiomyocyte from iPS cells for a year, and they are certainly mature but not as ideal. Hormones can drive, or you actually alter serum energy source. If you actually have only glucose in the media, you probably want to consider putting some fatty acids. You have a cellular interaction, some of the matrix that allow them to contract more forcefully, or to align the cells with other heart cells to actually contract as a unit. Substrate stiffness, if it's too stiff, they won't be able to contract at their will. Um, so the biophysical stimulation, electrical stimulation has already proven that it's going to drive the cardiomyocyte maturations in vitro. So what's the road ahead for cardiac regeneration? We already discussed all the stem cells that we have. We already discussed the option we have. We also discussed the opportunity the induced pluripotent stem cell actually offered. And what's next is more into like how we actually put it together to make it into like a tissues where you have a good cell maturity. You have the engineering techniques that are actually compatible with the delivery methods, whether we're actually transplanting and make sure the drug survive. We need some of the cellular components, the combinations of cells, not just the cardiomyocyte, but also the fibroblasts, endothelial cells, or small muscle cells. It will actually help with angiogenesis or revascularizations in your graft, and also, of course, the extracellular matrix that is essential for attachment and the cellular organizations. So there are strategies to engineer a tissue or to actually rebuild the heart. I can actually talk more about that. Um, so if we have a matrix, the cell can actually adhere, they align to according to the structures of the matrix, then we get more of the cardiac, myocardium-like tissues, and also those matrix should help or promote uh, 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 vascularizations after transplantation with the structures that they can offer. Um, I actually work with visualizations, and I actually find it very fascinating. I think that the limitation with the cells in hydrogel is that you need more of the cells component role in actually organize the cells in the way that you want. I think most of the engineered heart tissues are doing that methods where you actually cut it with the two silicone posts, and then when the cells, the cardiomyocyte seeded together with some fibroblasts at a certain ratios, they actually compact the constructs, and then actually get to contract by holding to the silicone port that's flexible. That actually gives some exercise to the heart tissues, and it actually matures over time. You can actually transplant it. I think a group in the UK is doing that. Um, in terms of deserializations, this is the technology where we actually wash off all the cells from the matrix, from the heart, and leaving only the matrix behind, which is natural. We remove all the DNA components with the detergent and the solutions that we actually designed. And we are able to infuse the cells back to the heart and reserialize them. This is a very uh, uh, highly technical, challenging method to rebuild the heart by extending only a cardiomyocyte. Certainly, it's not possible. We also need to know the clues of how we have the right cells in the right spot during the visualizations. We also need to know how we can actually direct some of the uh, non-cardiomyocyte cells in the play, and how we actually restructures um, or increase the restorized hearts, the complexity, the structural, functional um, uh, restorations of the heart. Although some of the study has shown the possibility to actually restore the heart from using the cells in the digital matrix in rats, larger scales on a human myocardium um, it still requires more the research to look into how those limitations can be overcome. Alternatively, we can actually put the cells together with the right cell, right spot, spatial and temporally using a 3D printers. Um, 3D printing is fine. I think it is also has a limitation of printing the blood vessel, especially the microvessels. Uh, I believe over time, when the technology has evolved, we are able to actually make vascularization of the tissue constructs, whether using the digital matrix or 3D printing, we should be able to engineer much thicker cardiomyocyte or myocardiums for regenerations. And the key lies with the perfusion of the contrast. So one of the projects I did together with a group in Harris Art group in Harvard Medical School is to re-cellularize the human heart and then look into how the cardiomyocytes survive, how they actually re-cellularize, and we are also looking into the cellular and structural complexity, how we can actually overcome some of the limitations. We have actually preserved most of the native vessels, the canals for blood vessels. We just need to revascularize those vessels with the right cells, and then we inject those cells, the cardiomyocyte, into it with all the blood vessels already there. So we are able to actually envisage a much thicker and cardiac construct using this method. But how do I actually put it in a more defined way, more organized way? It's still under investigations. So the conclusion for my talk today is that what we have to achieve so far and what do we look forward to. The adult stem cells have limited regenerative capacities owing to the lower differentiation plasticity because they won't be able to form most of the time, not able to form functional cardiomyocytes. Paracrine effects are proven to be the primary mechanism for the functional benefit we observe in adult stem cell therapy for heart failure patients or acute myocardial infarctions. Human-induced pluripotent stem cells are by far the most and only feasible cell source for cardiomyocyte generation and production for therapy. Advances in driving immaturity and differentiation efficiency, and also the purity to make chamber-specific cells may improve its therapeutic efficacy with reduced risk of arrhythmia. Considerable progress in generating engineered heart tissue with high cellular and structural complexity warrants therapeutic use to treat patients with heart failure. So with this, I thank for your time listening to my talks, and thanks to the organizing committee for inviting me to this event. Thank you.